7. You have to pass your examination. Attention, please. Bon, okay. We start. Can you find the page 40 of our file seminar number 4?
Which page again?
40. Not 14, but 40. Exercise number 27, slide 1.
Okay, perfect. I'm there.
Michael. So here we have an exercise which concerns the limit of nth root of n. We have discussed this last time. So now we have to remember that the limit as n goes to infinity of the nth root of n is 1. The exercise is very simple. So you have 1, 2, 3, 4. You see, the first statement is we want to find the limit of x over n, where x over n equals nth root of n squared. Second problem. You have x over n, which is nth root of sin n, 5n, excuse me, 5n. The third problem. Here you have that x over n, x sub n, is the 2nth root of 2n. And finally, the fourth problem is x sub n is the 4nth root of n. So we start from the very beginning. So we consider the problem number 1 or the statement number 1, I don't know. So in this case, we make use of our result from the exercise number 26, namely that the limit of nth root of n as n goes to infinity is 1. In this case, we can represent our x sub n as the product of the nth root of n by nth root of n. In this case, in fact, we make use not only of the exercise 26, but also of the limit theorem. So in this case, I know that the nth root of n is 1 multiplied by the limit of nth root of n. So the limit of my sequence x sub 1 is 1. Is it clear?
Yeah, it's clear. Makes
In
sense.
the first exercise, yes?
I hope that it is very clear, but do not forget in your beginning, in your in the beginning of our work that there exists the limit theorem. You see, it is important. After this, you will do it automatically. But now, do not forget about. Clear? So now, as for the problem number 2. So in this case, we have to use two results. The first one is the exercise number 6, where it is proved that the limit of the nth root of a, where a is strictly positive, is 1. And also we make use of the exercise number 26 as for the nth root of n. So we turn our page and we represent our x sub n as a product of nth root of 5 and nth root of n. So we do not forget about the limit theorem. We know that the limit of the nth root of 5 is 1, and the limit of nth root of n is also 1. So the limit of our sequence x sub n is 1. But do not forget also about an important thing. You see, you can apply your limit theorem if in this case at least if these two limits exist. So I know that the limit of nth root of 5 exists, and I know that the limit of, and you know also, excuse me, and the limit of nth root of n is also 1. So I can write that the limit of the product is the product of the limits. So in this case, it will be 1. Is it clear? Maybe you have some questions. No?
It's clear.
It's clear.
Valentina, it's clear.
Yes, it's clear.
Very good.
Yes.
Merci. Gracias. So let's consider the problem of the statement 3. So in this case, we have maybe rather sophisticated sequence, which is 2n root of 2n. So we have to rearrange the representation of our nth term of the sequence. In this case, first of all, I write that x sub n is 2n to the power 1 over 2n. It is the same thing. Then I write that it will be 2n to the power 1 over n, and all this to the power 1 over 2. Is it clear? As for the powers, how to work with the powers?
Yes, Professor.
Yeah. Eric, is it clear?
Yes, it's clear.
I tried
Yeah.
it.
So now, I write only for you that in fact we have the square root of 2n to the power 1 over n. Now, let's recall that if we have a sequence y over n which converges to some positive number a as n goes to infinity, then we have that the limit of mth root of y sub n is the nth root of a. So this is a formal thing, and only now then you will understand and you will work with these sequences automatically. But now I want to explain you how it works. So in this case, I introduce the sequence y sub n, which is 2n to the power 1 over n. Then, as in the previous example, what do we have? We have that the limit of y sub n is the limit of nth root of 2 multiplied by nth root of n. So we have to use two exercises because, I repeat, you know that the nth root of 2 exists, nth root of n exists, they are 1, so the product will be 1. Then you turn your page 42. Then you see, I know that my sequence x sub n is exactly the square root of y sub n. So the limit of x sub n will be 1 due to our exercise number what? Oh, from the formula 4.8 from the page 41. Is it clear?
Yes, Professor, it's clear.
Thank you.
Yeah, Professor, it's clear.
Yeah. So the last statement here is the statement of the problem number 4. We have a similar situation. So first of all, we represent our x sub n as the 4nth root of n. Then I can write that it will be nth fourth root of y sub n, where y sub n is nth root of n. The arguments are clear.
Yes, all the arguments are clear. It makes sense.
When I came,
So no problems. Then, as in the previous statement, you have that the limit of your sequence x sub n is also 1. So really a simple exercise. I hope you understand all this. Now, you turn your page. It's number 43. Here I want to formulate for you the monotone convergence theorem. It is an important theorem because, you see, in some way, maybe we do not know how to calculate the limit of a sequence, but theoretically, we know that the limit exists. Why? One of the ways here is this monotone convergence theorem. So, formulation. Let x sub n be a sequence of real numbers. Then we have two statements. If x sub n is an increasing sequence, and in addition, it is bounded above, then this sequence is convergent. I don't know, maybe you have your lectures, and you have the explanation of maybe the proof of this theorem, but if you take a pen and in this case, you take a sequence 1 minus 1 over n. Then you see that as n goes to infinity, this sequence is increasing. And also, it is bounded by 1. So this sequence is convergent. Is it clear?
Yes.
Yes.
Good. Monia, c'est clair?
Oui, c'est clair.
Merci beaucoup.
Je vous en
In a similar way, we say that if x sub n is decreasing and bounded below, then it is also a convergent sequence. Here you can have an example that the sequence x sub n 1 over n is a decreasing sequence. It is clear. If you use your calculator, you can see this, and also you can prove this easily. But also, all the terms of this sequence are positive. So we have a decreasing sequence, and this sequence is bounded below. So this sequence is a convergent sequence. And now I hope you know that the limit of this sequence is 0. Clear?
Yes, it's clear.
Good. Très bien. So we turn the page, and maybe I hope that in your lectures you have the notion of the number e. By the definition, we see that this sequence x sub n is defined as 1 plus 1 over n to the nth power. So in this case, you see, we have an indeterminate determinate form like 1 to the power infinity. You see, in this case, I know that 1 plus 1 over n goes to 1. Yes, and the power n goes to the infinity. So we cannot say that in this one some power is also 1, because here really we have an indeterminate form like this. So if you are not agree, you can take your calculators and try to find some first values of this sequence. You will see that this sequence goes to some sophisticated value, which is called E, due to the name of the famous mathematician Euler. So, in order to prove this theorem, we use the monotone convergence theorem. This theorem enables us that the limit exists, and then we can calculate this limit. The number E is given below. So it is not necessary to know the exact, even in this form, the value of E, but you have maybe in your head, and for physics, you have to know that E is 2.7, or another decimals. I think we use only for numerical simulation. I'm not sure, but I hope. So it is for here. It is only for the information. We will use these results. We will use this result later in the following exercises. So you turn your page. It's the page 45, and we have another limit to remember. The classical limit, which is given by the formula 4.11. So the limit of where n to the power n is 0. So first of all, we will use, I will say when, the monotone convergence theorem. And we will see that the proof of our limit 4.11 is done in 3 main steps. First of all, step number 1. We want to show that our sequence x sub n is monotonically decreasing. How we can do this? You see, if I take the ratio x sub n plus 1 over xn, if this sequence is decreasing, this ratio have to be less, strictly less than 1. You see? Agree?
Yes, I
Yeah.
agree.
Agree.
Yeah.
Very good. So I have my formula for the term x sub n plus 1. And I have to divide this by x sub n. So I write n plus 1 factorial divided by n plus 1 to the power n plus 1. So the first term is evident in this product, evidently. Then I write something like 1 over x sub n. It will be n to the power n over n factorial. Clear?
Yes, it's clear.
Clear. So,
Yes, it's clear.
good. Now we can reduce our fraction. So you see that n plus 1 factorial is n plus 1 multiplied by n factorial. And n plus 1 to the power n plus 1 is n plus 1 or n plus 1 multiplied by n plus 1 to the power n. Then we have the product n plus 1 over n plus 1 multiplied by n to the power n over n plus 1 to the power n. Is it clear?
Yes, everything's clear so
Clear.
far.
No problem. So this fraction is in fact is n over n plus 1 to the power n. And this quantity is less than 1 because n is less than n plus 1. Clear?
Yes, it's clear.
Clear.
Yes.
So we have from 4.12 that x sub n plus 1 is less than xn. And the conclusion is that this sequence is decreasing. Clear?
Yes, it's clear.
It's clear. Good. So you turn the page. You turn the page. We have, if you take the definition of our sequence, you can see that for all n, x sub n is strictly positive because here we have only n factorial n to the power n, so the sequence is always strictly positive. Now, from our monotone convergence theorem, what do we have? We have that our sequence x sub n is decreasing and bounded, and it is bounded from below. So at least we have a conclusion that there exists a limit of our of our sequence x sub n. I don't know the value of this limit for the moment, but I know that this limit exists. So the last step is to identify the limit of our sequence. So you see, you turn, if you take the formula 4.12, you will see that x sub n plus 1 is n over n plus 1 to the power n multiplied by x sub n. Is it clear?
Yes. Yes.
Très bien. So let us denote the limit of our sequence x by capital L as limit. So if we take our relation 4.13 and we pass to the limit on the left hand side and on the right hand side. So we hope that if the limit of the sequence n over n plus 1 to the power n exists, only in this case, you see, the limit theorem works here. This theorem also works. So on the left hand side, the limit of x sub n plus 1 is L, capital L. I hope it's clear. So I write here that as for this sequence n over n plus 1 to the power n, I write only the limit. For the moment, I do not know, I have no information about the existence of this limit. But as for x sub n, I know that the limit is also L. So we have this relation. Now, if you turn, if you know, if we can show that n sub n to the power n over n plus 1 over n converges to some real number r, then we can write our previous relation in the following form: L equals R multiplied by L. So you see, in this equation, in this simple equation 4.14, if R is different from 1, the only solution to this equation is L equals 0. Is it clear?
Yes, it makes sense.
No problem. Très bien.
Yes.
So our goal now is to calculate the limit of the sequence n to the power n over n plus 1 to the power n. So we can see that n to the power n over n plus 1 to the power n is exactly n over n plus 1 to the power n, or I can write this as a fraction, 1 over n plus 1 over n, and all this to the power n. Is it clear?
Yes, right so far it is right now.
It's clear. So now we rearrange the denominator of our fraction, and I write that it will be 1 over, in my denominator I have 1 plus 1 over n, and all this to the power n. So the final result here in this equation, in this representation, is that our sequence is 1 over 1 plus 1 over n to the power n. Then, due to the definition of the number e, we know that the limit of the sequence n to the power n divided by n plus 1 to the power n is 1 over e. Is it clear?
Yes, it is.
Yes, it is clear. Yeah. So if we return to our equation 4.14, then we have that 1 over e is not 1. It is something which is less than 1, in fact. Yes? Then the only solution to this equation 4.14 is capital L equals 0. So by our notation, the limit of the sequence x sub n is capital L, and we prove that this limit is 0. Then we have proved that the limit as n goes to infinity of n factorial over n to the power n is 0. So this exercise in this way is completed. The questions. The question. The questions. Or it is clear. Onya, c'est clair?
Oui, c'est clair.
Yes.
Merci
Clear.
beaucoup. It's clear. Thank you. So now we turn our page. And we will consider another limit to remember. So it is exercise number 30, slide number 1. It is a rather sophisticated, maybe in some way we can forget about some details, but I want to show you how to prove estimate the inequalities, because it is very important to know how to estimate your sequences, and not only the sequences, but in future the functions, because the estimates, the inequalities, it is an important tool in the mathematics. You see, so it will be maybe for you rather long, but I think it will be useful. So you see, in order to prove our limit 4.15, we will use some inequalities. So for the moment, you do not know how can I use this inequality, but you will see this immediately or in 10 minutes. Not immediately, but in 10 minutes, I hope. So the first inequality. You see, this is the inequality number 4.16. I want to prove that n factorial is greater than n over 3 to the power n. So in this case, I hope you have some ideas of the method of mathematical induction. So in this case, we can use, as usually, in the case when we have some inequality or some equality with a natural n, so the method of mathematical induction is very useful. In this case, if I take n equals 1, then 1 factorial is 1, and n over 3 to the power n is 1 over 3. So this inequality holds true. No problem, as for n equals 1.
But why is divide by 3 in the equation?
It's a good question. You see, all this comes from the number e. It is not. It comes from the number e. I hope that I think that if you take the inequality n over 4, this inequality works also. But 3 in this case, if you want, it is not an explication, roughly speaking. It is in some way a limit number. You cannot write n over 2 power n. It is not right. But n over 5, you can. Will be also good as for this inequality. You see, Valentina?
Yeah. Okay.
So all these examples come from the number e. In some way, we prove that the limit of plus 1 over n to the nth power exists, and so on and so on. You see, so we follow some lines of this proof, but in another exercise. You see, so we will do this.
Okay.
Okay? So 49. We suppose that our inequality is right for n equals k. Is valid for n equals k. So the last step of the mathematical expression is to prove that it is good if I take n equals k plus 1. You know this, yes?
Yes, we know.
Oh,
Yeah, you know.
good, good. So, what I have to take? I have to take k plus 1 factorial. Then it will be k factorial multiplied by k plus 1. You see, as for the k factorial, I have my assumption, supposition that k factorial is greater than k over 3 to the power k. And it is multiplied by k plus 1. Is it clear?
Yes, it's clear.
Yes, it's clear.
Yes.
So now, I want to estimate this quantity from below. So the next line. I write k over 3 to the power k multiplied by k plus 1. So in this representation, you see, in this representation, in red, I take only the terms which I need. Because you see, what do we want to show at this step? That k plus 1 factorial is greater than k plus 1 over 3 to the power k plus 1. So in red, I have exactly the term or the term which we need for our mathematical induction. The second term in this case will be 3 over 1 plus 1 over k to the power k. Okay, is it clear?
Yeah, yeah, it's clear.
Just a moment, somebody.
Yeah, no problem.
Only one moment. Mhm. Okay, so at this step, you see the second term in this product is 3 over 1 plus 1 over k to the power k. So if we know that the limit of this sequence is e, so in this case, the proof will be finished because 3 over 2.7 something plus it will be good for the proof. But imagine, suppose that we do not know the limit of this sequence. Is it clear? So here I add something in our exercise to show you one more inequality, which is also useful in the mathematical analysis. Is it clear here?
Yeah, it's clear.
It's clear. Now you see, Eric,
Mm-hmm.
in the proof of the convergence of the sequence, or in the proof that E is really E, as it is written, we use, if we turn our page, we have the page 15, we have the inequality number 2. So we want to prove that 1 plus 1 over k to the power k is less than 3. In this case, you see, in the last formula, at the page 49, this term is greater than 1. So we have our desired inequality. How to prove 4.17? You see, it is the chance that we have a natural number k, so we can use the binomial theorem. I rewrite my term 1 plus 1 over k to the power k as a sum. Do you remember the situation with the binomial theorem? I hope you can check this formula, because we have discussed this. So I write 1 plus 1 over k as 1 plus k over k plus k multiplied by k minus 1 over 2 multiplied by 1 over k square, and so on and so on. And then, you see, as for the first term, 1 is 1, no problem. K over k is also 1. Then I have 1 over 2 factorial. And you see, you have here a fraction, k multiplied by k minus 1 over k squared. So we divide each term in the numerator by k. And then we have that it will be 1 minus 1 over k. Is it clear?
Yeah. Mm.
Very
Yes.
good, very good.
Okay.
Très bien. So in a similar way, you have for the term, for the case term, you have that it will be 1 over k factorial multiplied by 1 minus 1 over k, so on, 1 minus k minus 1 over k. Is it clear? You see,
Yes.
as for the last term, you have something divided by k to the power k. So we have this product. Now, you see 1 minus 1 over k is less than 1. Agree?
Yes, I agree with it because it's different from the other inequalities.
It is evident.
Yeah.
So we have in this way, we have our inequality that 1 plus 1 over k to the power k is less than 1 plus 1 plus 1 over 2 factorial plus so on 1 over k factorial. Okay? So the inequality 4.18. Clear, Eric?
Yeah, I'm looking at it right now. So no, yeah, it makes sense. It does. I see it.
On y a. Est-ce que c'est clair?
Oui, c'est très clair.
Yeah. On y va. So you turn your page, you see for the moment, and you have to know this, all these inequalities, because they are very useful in mathematical analysis. So we have to estimate the right-hand side of the inequality 4.18. How we can do this? In fact, we want to use the geometrical progression. But how? How? The method, this approach is, I claim that k factorial is greater than or equals 2 to the power k minus 1. So the inequality 4.9. 4.9. This inequality I want to prove by the method of mathematical induction. So you see that if I take k equals 1, then 1 equals 1, or I can say that 1 is greater than or equals 1. So as for k 1, everything is good. Now I suppose that for some k which is equal to m, my inequality is true. Then yeah, I have to prove this inequality if k is m plus 1. Now I take m plus 1 factorial. It will be m plus 1 multiplied by m factorial by the definition of the factorial. From the previous step, I have that m factorial is greater than 2 to the power m minus 1. So I have m plus 1 by 2 to the power m minus 1, and this product is greater than 2 to the power m. Is clear?
Yeah, it's
Yes.
clear.
No problem. I hope. I think. So we turn the page. Now we return to our inequality. what do we have? We have 1 plus 1 over k to the power k is less than 1 plus 1 plus 1 over 2 factorial plus so on plus 1 over k factorial. Then, by the inequality 4.19, we can estimate the terms here by 1 plus 1 over 2 plus so on plus 1 over 2 to the power k minus 1. I think it's clear. We just apply this inequality 4.9, nothing else.
Yeah, it's clear.
Clear. So I claim that the underlying sum is less than 2. So this sum, the whole sum is less than 3. Why? Here, in fact, you have a geometrical progression. So I have written this. So you can find the sum of the geometrical progression or the sum of the first n terms of this progression, and you will have that this sum is less than 2 in this case. You see, because it is a special case of the geometrical progression, maybe in other case it will be another value. Attention. Do not forget about this. So what do we have? We have that our sequence 1 over nth root of n factorial. First of all, it is strictly positive, greater than 0, and also due to our inequality, the first one, the inequality 4.16, it is less than 3 over n. Now, as usually, we have two ways. First of all, even here, I write that it is less than epsilon. So I have to find my cutoff capital K such that for any n greater than this capital K, which depends on epsilon, our x sub n will be less than epsilon. Another point of view to this problem is, in fact, we can forget about epsilon and we can use the two policemen theorem. So on the left hand side we have 0, a constant sequence which goes to 0. On the right hand side we have a sequence 3 over n, which is the sequence which goes to 0 as n goes to infinity. So in both cases we have the desired limit 4.15 is 0. So the exercise 30 is proved. Is it clear?
Yes, yes, that it was clear in the last part. Makes sense.
Mm-hmm. Good. Onya, est-ce que c'est clair?
Oui, c'est clair.
Yeah. So now you turn your page, then I want to recall maybe once more, but in this case you have a written form of this theorem, two names, two policemen theorem or squeeze theorem. So if I have three sequences with the following properties, that a sequence B sub n is greater than or equals an, less than or equals cn for all n natural. You see, in this case, attention, it is an important remark because if for the first terms, for some finite number of terms, this inequality is not valid, but it is valid beginning from some natural number n0, and for all n greater than n0, it will be enough because we are looking for a limit and not the first terms, a finite number of first terms of a sequence, it is not very important. So we can say that this inequality holds for all natural n beginning from some natural n0. Is it clear?
Yes, yes, it's clear.
Yes.
But it is very important that maybe you can see in some inequalities that for the first terms it is not valid, but if it is valid beginning from so on, you see, don't forget about. Then the conclusion. If I have that the limit of a sub n and c sub n is L, then we have that the limit of d sub n is also L. No questions, no problems. So now we turn our page, and we pass to an exercise on the number e. So in this case, we have an undeterminate form like 1 to the power infinity. And we want to use here our knowledge about the number e, or our knowledge about the limit of 1 plus 1 over n to the power n. So, you see, first of all, we want to find the limit, we want to calculate the limit of the sequence x sub n, which is 1 plus 1 over n squared to the power n. So it is not exactly like in the definition of the number e. So we have to rearrange our nth term of the sequence, and we rearrange it in the following way. So you see, I write that 1 plus 1 over n squared to the power n is in fact 1 plus 1 over n squared to the power n squared, and all this to the power 1 over n.
I don't understand very well this part.
Pardon? Valentina, where
Yeah.
is the question?
How to put this following equation? M 1 over n.
You see, Valentina, I want to use my definition of the limit. And in this definition, 1 over something have to be in the same power.
Okay. Okay.
This is why I use. You see, nothing changes. I have the same thing, but in the square brackets, what do we have? We have 1 plus 1 over n squared to the power n squared. And all this to the power 1 over n. You see, n squared is also a natural number. So if I denote n squared like m, for example, you see, I will have that the limit 1 over 1 plus 1 over m to the power n will be e. So n squared plays the role of some natural number. No problems.
No
Is
problem.
it clear? Because
I have another question. If I have, for example, no one, for example, 2 over n power on the power 2 is the same or change something?
you see, if you have, for example, we forget about our. It is my mistake. Okay, so if you have, for example, if you have 1 plus a over n to the power n, and we are looking for the limit. Here is the question, yes?
Yeah.
So you a, for example, it is not necessary, but for example, a is a positive number. So you rewrite your limit in the form like here, 1 plus 1 or a over n to the power n over a. And all this to the power, you see?
Yeah.
Is clear. So you have to, we can discuss this. We can discuss this, maybe it will be useful because I've forgotten about, excuse me.
So is a is any natural number?
No. It is not important here.
Okay.
Because in the case of positive and negative number, you will get 2 different answers if you want, 2 different limits. We will discuss this, okay?
Okay.
Because now I want to give you some very simple examples in order to understand the method. And the method is to use the definition of this number e. Now, in the square brackets, I have a sequence. Yes? I want to denote this sequence by 1 over n. So I have 1 over n to excuse me, I have y over n to the power 1 over n. Yes? So something in the square brackets I denote by 1 over n. So my x sub n is y over n to the power 1 over n. Clear? Eric,
Yeah,
clear?
it's clear.
Nothing else since the notation.
Mhm.
So if we consider the sequence y sub n, first of all, it is greater than 1. Yes? Strictly greater than 1 because it is 1 plus something to some power and square. So it is greater than 1. And it is less than e, because we know that the limit of this sequence is e. So we can write this inequality. Y sub n is greater than 1 and less than e. If you do not, attention, in this case, I can also write that this y sub n is less than 2e or 3e or 4e. You see, it is not a problem because next we have to calculate the nth root of these sequences. But at least we know the limit of our sequence y sub n. So it is less than e. So
It's clear.
it's clear. Good. So the next step is absolutely clear. We take the nth root of 3 parts of this inequality, and we have that x sub n, which is nth root of y sub n, is less than e to the power nth root of e. Nth root of e. Okay? Then, first of all, the nth root of e. E is a positive number. Then the nth root of e goes to 1 as n goes to infinity. 1, the nth root of 1 is always 1. So, 2 policemen theorem says that the limit of my sequence x sub n goes to 1. So the answer of in this exercise is that the limit as n goes to infinity of xn is 1. Is it clear?
Yeah.
Yeah.
Also, is there a tiny
So now, before the last step in our seminar, we have a break 10 minutes and then we will continue. Agree?
Yes, sir.
Yes, agree.
Yeah.
Professor, can I ask something in the break?
I think because we have not a lot of pages to discuss, so I think we can discuss this problem with xn, yn, which go to 0 and so on and so on. We can discuss this if you want. I think it is good to discuss this only with a pen, not with my notes. Agree?
Yes, I agree.
So we will finish this part, and then we will discuss this home task. Okay?
Okay.
Okay,
Okay.
Valentina.
Yeah,
Good.
yes, okay.
Good. On y a. D'accord?
D'accord.
D'accord. Donc, à plus.
À plus.